In this lecture, we are going to take one numerical problem on threshold voltage. This is a very classical example because in this example, you can use most of the formulas which we have discussed till now. What is the problem? The problem is given for n-channel MOSFET, these are the parameters given to you. Number one, Na, doping density of the substrate. Doping density of the substrate. So as soon as you see that it's a Na, you can immediately understand that this is an n-channel MOSFET. Why? Because if the substrate is P, definitely this is going to be a n-channel MOSFET. So the substrate doping density is given as 4 into 10 to the power 20. ND meaning as soon as both Na and Nd is given, you can immediately understand that it's a polysilicon gate. It's not a metal gate. You can immediately understand this. What is the density given? 2 into 10 to the power 20 per centimeter cube. And what is the T oxide? And that means oxide thickness is given as 16 angstrom. NOx, defect density in the oxide region, is given as 4 into 10 to the power 10 per centimeter cube, per centimeter square. We have to calculate the threshold voltage, which is at VSB equal to 0. This kind of a problem normally you can solve in 5 to 6 steps. Because if you see the formula for Vt naught, so Vt naught ka formula let's write over here. So Vt naught is basically equal to phi Gc. So in one step you calculate phi Gc. In another step you calculate the 2 phi f. In another step you calculate the QB naught divided by Cox. In another step you calculate the Qox divided by Cox. So basically in one step you can calculate this, another this, then third step this, fourth step this, and the fifth step you can calculate Cox, and finally you can calculate the Vt naught. So normally 5 to 6 steps this kind of a problem takes. So step 1, since it's a polysilicon gate, let's calculate phi f of substrate and phi f of gate. These two we need to calculate. We already know what is the phi f. Phi f is a Fermi potential. Fermi potential we always calculate by kT by q ln ni by na. Okay, for the substrate, since it's Na, so Na will be in the denominator. So kT by q, it's a room temperature. At room temperature, kT by q is always 26 millivolt. Then you have a ln. What is Ni? Ni is the intrinsic carrier concentration, which is always constant for a silicon at a particular temperature, which is given as 1.45 into 10 to the power 10. So 1.45 into 10 to the power 10 divided by 4 into 10 to the power 8. So when you calculate it, it comes out to be 0.51 volt. So this only corresponds to the substrate. But now, do we need to calculate for the polysilicon gate also? In principle, yes, we need to calculate the ND also. But since we know, this is the fact, we know that if in the semiconductor silicon you have, in the silicon semiconductor you have doping level 10 to the power 20, you can directly put ND value is 0.55, because we know that in a silicon semiconductor, if the doping density is 10 to the power 10, the Fermi level lies somewhere in between the band gap. And as soon as you increase the doping, the Fermi level goes closer to the conduction band if it is the n-type semiconductor. So when you have doping 10 to the power 20, it's exactly at the conduction band level. It matches exactly with the conduction band level. So this is, you can directly put, whenever you see that the doping density is 10 to the power 20, you can directly write, without calculating, you can directly write it's a 0.55 volt. So in the first step, we have calculated the phi Gc. What is the phi Gc? Phi Gc is always phi f of substrate and then phi f of the gate. So what is that? So 0.51. This is how it is defined already, because in the formula we are taking this as a positive quantity. So we need to define, we have already defined this, that phi f substrate minus phi f of gate. So when you calculate it, minus 0.51 minus 0.55, it is equal to minus 1.06. Now in the step number 2, we have to calculate 2 phi f. Phi f is already calculated. This phi f is also belongs to the substrate, not to the polysilicon gate, because in the substrate itself you need to make the changes. You need to make the P to N. Inversion has to be done in the substrate. So next step, you have to calculate the 2 phi f, which is very easy. Only one line step. So phi f you have already calculated. It's a 0.51. So the total 2 phi f will be minus 1.02 volt. Now in step 3, we need to calculate the QB naught. QB naught is already, we know that minus under root 2Q Na epsilon Si and minus 25F. When you will put the values, because you already know 2, you already know Q 1.6 into 10 to the power minus 19, Na is already given 4 into 10 to the power 18, epsilon of Si is epsilon of R 11.7 into multiplied by the permittivity of the free space, which is 8.85 into 10 to the power minus 14 farad per centimeter square, multiplied by mode of minus 25F, which is minus 2.05. When you solve it, it comes out to be 1.16 into 10 to the power minus 6 coulomb per centimeter square. So this is the charge density in the depletion region. Similarly, now since in step number 3 you need to also find out the COX also. So COX will be epsilon OX divided by TOX. So and similarly, epsilon OX is a relative permittivity of the oxide, which is 3.97. The permittivity of the free space is again 8.85 into 10 to the power minus 14 divided by TOX. TOX is 1.16 into 10 to the power minus 7 centimeter. It was given in angstrom, 16 angstrom. So we need to convert this into centimeter. So finally you got 2.2 into 10 to the power minus 6 farad per centimeter square. So in step number 4 you have already calculated COX, which will be needed in term number 3 and term number 4. Now you have to find out the QOX, the oxide density. Only so the number of charges density was given, that was 4 into 10 to the power 10. So every defects or every charge has to be multiplied with the charge of the electron. So then only you will get the total charge per centimeter square. So 1.6 into 10 to the power minus 19 multiplied by 4 into 10 to the power 10, which comes out to be 6.4 into 10 to the power minus 9 coulomb per centimeter square. So this is your total oxide charges in the oxide layer. Now step 6 is the final step, where you put all the terms together. So VT naught, we already know there are 4 terms, 5GC number 1 term, 25F number 2 term, number 3 is QB naught divided by COX, number 4 is QOX divided by COX. When you put all these values, so this is already in minus, so keep in minus. So these values, the values of these quantity, you have to put with the sign also. So when you put with the sign and you calculate it, it comes out to be 0.487 volt. So this is the threshold voltage of this particular MOSFET, where you have the doping density of the substrate around 10 to the power 18. Okay, mostly this VT naught depends upon the materials property, like what is the doping concentration and all. So this comes out to be 0.5 volt. Thank you.